So I'm going to talk today about the future of subsurface manufacturing, and that's really a mouthful. So I like to think of it as the future of energy. And in order to talk about the future of energy, we have to go way back to the very beginning. Now this cartoon here does a pretty good job of depicting the origin of oil. After all, I got it off Facebook, so it has to be true. But my biggest complaint about this cartoon is that it doesn't discuss the microbes that were involved in the process. So a lot of people still think that the biomass that formed the majority of the oil that we find today came from dinosaurs and plant matter, big plants, when in fact the majority of the biomass that formed the oil that we find today came from microorganisms. So phytoplankton and algae, they would bloom in the ocean, they would die off, their biomass would fall to the bottom of the ocean, they'd be covered by sediment, there'd be more blooms, more biomass, more sediment, and eventually over time, over hundreds of millions of years, you add heat and pressure, and you get oil. Now, over those hundreds of millions of years, there are also other organisms that were feeding on and consuming the biomass and the oil in place that were degrading and shifting and shaping the oil into what we find today when we drill for oil. Now, there are also microbes that have been living in the reservoir the whole time that produce negative side effects to oil and gas production. So they can produce H2S, or hydrogen sulfide, which is a deadly toxic gas that kills hundreds of people in the oil and gas industry every year. They can biofoul membranes and various parts of the production system. And they can also cause corrosion in a process known as microbiologically influenced corrosion. So I titled this slide Corrosion IRL, and if you're not a millennial or younger, IRL means in real life. And I called it this because these are all photos that I actually took in my previous experience, which I'll touch on more here in a minute. But every single one of these pieces of piping and metal, tubing, vessels that are corroded here, this was all directly caused by microbes. And the cost of damage from microbiologically influenced corrosion is estimated to be $500 billion, with a B, dollars every single year. So in order to mitigate the negative aspects of these microbes, H2S and corrosion, oil and gas companies pump biocides. Now, if you're not up to date on your Latin, bio meaning life and side meaning killer of, a biocide is a substance that destroys living things. So oil and gas companies pump these toxic substances into their oil and gas streams, into their water streams, into their vessels, and the purpose is to kill the microbes that can cause H2S and corrosion. Now, the toxicity of these microbes or toxicity of the biocides are determined by how much or how little of the biocides it takes to kill mice or rats, or in the old days, bunnies even. And this is where I come into play. Not necessarily killing bunnies, but in petroleum microbiology using biocides. So I spent the first 7 years of my career in petroleum microbiology. I was largely responsible for developing molecular methods to enumerate and characterize microbes in the oil field, so determine how many microbes are there and what they are, so we know that if there's a risk of H2S or corrosion. And then more importantly, I would formulate, qualify, and apply biocides into production systems in order to kill the microbes. So in short, I spent the first 7 years of my career killing microbes in the oil field. Now, at some point, I took a step back, and I kind of decided that this wasn't necessarily the most sustainable career path in my still relatively young career, right? So I started looking for how I could apply my knowledge and experience and know-how of subsurface petroleum microbiology to do something better and more sustainable. And that's how I found Cemvita. So when I first came to Cemvita, the team in Moji was really looking at can we turn subsurface reservoirs into chemical plants? And we first started, the team when I joined, was looking at how can we create methane in the subsurface. And there are other players in the game looking at how we can couple CO2 injection for CCS, carbon capture and storage, and get methane out of the ground using microbes. Now, most of the other players were looking at co-injecting hydrogen along with the CO2, because in order to get methane, you need CO2 and you need hydrogen. We also thought that wasn't necessarily the most sustainable route for biomethanation, so we started looking at how can we create hydrogen in the subsurface to couple with the CO2 injection in order to get methane out of the ground. Once we realized that we could produce hydrogen, well, hydrogen is a much sexier molecule than methane, right? So we kind of just started rocking and rolling on hydrogen. Now, this was a study that came out in Nature about, a year ago maybe now. But the authors wanted to look at how much of the known oil and gas reserves would have to remain unextracted in order to meet the 1.5 C temperature change set forth by the Paris Climate Accords. And what they found was that 60% of all known oil and gas reserves would have to remain unextracted from the ground in order to meet that 1.5 C change goal. Now, while at the same time, it's expected that by 2050, there's going to be a 60 times increase in the demand for a low-carbon hydrogen product. So this really leaves a huge potential in order to, if we can take the hydrocarbons that are increasingly unextractable from the ground and produce a low-carbon hydrogen product from those hydrocarbons. And that's exactly what Cemvita is trying to do with gold hydrogen. So we define, if you've been living on a rock and you don't know what gold hydrogen is, we define gold hydrogen as hydrogen that is produced biologically and in the subsurface. So we target depleted reservoirs, and when I say depleted, that means reservoirs that aren't necessarily producing economically amounts of oil, but there's still 50 to 70% of the remaining oil or original oil in place left in the reservoirs. So there's a large bank of hydrocarbon left in the ground that we can tap into. So we apply our microbes and nutrients into the reservoir. The microbes ferment the crude oil in place, producing hydrogen and CO2. Now the CO2 we leave in the ground, never to come up, and we produce the low carbon hydrogen out of the subsurface. So if we look at the wells in the United States, 40% of all US wells produce less than 1 barrel of oil per day. So they're very uneconomical. A lot of the oil and gas operators are producing them just so that they can retain the leases, hoping that in some future time, there's some innovation that allows them to more efficiently extract that oil out of the ground. So if Cemvita is able to target just 1% of these 40% of wells, we would be able to produce 1,500 tons of of hydrogen, hopefully not CO2, every single day. And that would equate to roughly $3 to $8 million in revenue every single day. So I might be a little biased, but I truly think that the future of energy is gold hydrogen. And the future is golden. Thank you.